Imagine you're trying to find a single lethal drop of a specific poison hidden entirely within a victim's bloodstream. Or picture trying to isolate just a microscopic trace of sulfur within the massive raging pipeline of a multi-billion-dollar oil refinery. How do scientists actually pull that off? Well, today in this explainer, we're tracking the fascinating evolution of the ultimate invisible detective, gas chromatography. We'll watch this incredibly precise analytical tool evolve from a delicate instrument sitting on a pristine lab bench into a rugged, fully automated system built for the absolute harshest environments on Earth.
Here is our roadmap for today. 1. Traditional GCMS and forensics. 2. The regulatory innovation catalyst. 3. Process GC in industry. 4. Integrating multiple detection systems. And 5. Micro GC and miniaturization.
All right, let's dive right into Section 1, Traditional GCMS and Forensics, the gold standard.
So, GCMS is essentially a hybrid technology. It's the ultimate magnifying glass for breaking down complex mixtures. But it does have one major constraint. The compounds you're looking at must be volatile and thermally stable. Basically, they typically need a molecular weight under 1,000 Daltons, meaning they are relatively small molecules. That way, they can be vaporized into a gas without just burning up or decomposing on the spot.
To really wrap your head around this, think of gas chromatography as a chemical sieve. A vaporized sample gets pushed by an inert carrier gas through a highly specialized capillary column. Now, these columns can sometimes be 30 meters long, yet they are incredibly narrow. As the oven temperature rises, the compounds inside separate out based on their boiling points. Then, those newly separated compounds enter the mass spectrometer, which is basically our fingerprint scanner. Here, they're instantly ionized and fragmented. The MS measures their exact mass-to-charge ratio, giving us an absolute, undeniable structural identification.
Because of this totally unmatched precision, GCMS anchors high-stakes forensic investigations. It's the final say in workplace drug testing to rule out false positives. Following super strict standards, it can sniff out trace accelerant residues, like gasoline, in fire debris for arson cases. It's also absolutely vital in post-mortem toxicology and anti-doping. In cases of drink spiking, where drugs are completely masked in complex beverages, GCMS can detect substances down to the nanogram per milliliter level. To put that into perspective, that's roughly equivalent to finding a single pinch of salt dissolved in an entire Olympic-sized swimming pool.
The real power here is legal defensibility. Consider the incredibly tragic Michael Jackson case. Post-mortem toxicological examinations utilize GCMS to detect lethal levels of propofol and lorazepam in some very complex biological samples. The reliability and repeatability of finding these specific molecular fingerprints are exactly what allow this data to withstand rigorous legal scrutiny in a court of law.
Moving on to Section 2, the regulatory innovation catalyst, forcing the evolution. So picture this. In May 2007, the EPA introduced Title 40, Subpart J. This regulation mandated significantly reduced sulfur emissions from petroleum refineries. Any new refinery built after June 2008 had to meet these strict new limits, and all refineries must comply by November 2025. This single mandate created a massive analytical crisis for the industry. Legacy, lab-based GCMS systems simply didn't have the sensitivity or the robustness to reliably hit these newly required trace detection limits continuously, especially not in a harsh, vibrating industrial setting.
So that regulatory pressure essentially forced the industry's hand. It triggered a rapid, hyper-concentrated decade of technological innovation. Engineers were forced to completely rethink the entire system architecture. They had to advance sample preparation approaches just to manage these complex chemical matrices and achieve cleaner, controlled sample transfers. Literally, the technology had to evolve, or it wasn't going to survive the new rules.
Which brings us nicely to Section 3, Process GC in Industry, out of the lab into the field.
You know, there is a stark operational contrast between a clean lab and a dirty field. Traditional analysis means you have to physically transport a highly hazardous sample from a pipeline all the way to a laboratory. This introduces delayed results, sample transport errors, and huge mismatch risks between what the lab sees and what's actually happening in the pipeline right now. Process GC, or PGC, flips this entirely on its head. These systems are built in ruggedized enclosures directly on or near the pipeline itself. They're integrated right into the plant's control systems to provide continuous, automated, online data with incredibly fast cycle times. Today, process GCs are absolutely indispensable for handling complex hydrocarbon streams, everything from light permanent gases up to heavy fractions.
They actively support natural gas custody transfer by figuring out the calorific value in real time. They monitor refinery fuel gas, and they ensure those ultra-strict sulfur recovery limits we just talked about are met instantly. This allows plant operators to continuously optimize the process without waiting hours for the lab to call them back with results.
All right, Section 4. Integrating multiple detection systems. The ultimate analyzer.
Modern, complex samples are tricky. Often, they require more than one set of eyes. Next-generation platforms solve this by packing multiple detectors into a single unit. You have flame ionization, or FID, which features a crazy wide dynamic range, making it highly sensitive and just perfect for hydrocarbons. Then you integrate that with mass spectrometric detection, or MSD, so you can grab structural fingerprints of complete unknowns. Finally, you add vacuum ultraviolet, or VUV, for ultra-high precision profiling of diverse analytes.
And here's the real kicker. To make this all work safely in a highly explosive environment, these advanced systems are ATEX and Class 1 Division 2 certified, which means they are completely explosion-proof. They utilize these highly precise convection ovens that enable reproducible retention times that are entirely comparable to a delicate, fragile laboratory capillary GC. It's just a phenomenal engineering feat, delivering lab-grade multi-detector analysis online inside hazardous areas with absolutely zero human intervention.
Finally, let's explore Section 5. Micro-GC and miniaturization. Power in the palm of your hand.
While Process GC was tackling the massive industrial plant, another breakthrough happened. The sheer scale of this miniaturization is staggering. Micro-GC, or mu-GC, takes that entire traditional architecture and shrinks it way, way down. Born from microelectromechanical systems, or MEMS research back in the 1990s, this tech required some major, groundbreaking leaps in microfabrication to actually become a reality.
Using this MEMS technology, engineers literally etch fluidic manifolds and tiny silicon-based columns directly onto wafers. They integrate ultra-compact injectors and apply highly sensitive microdetectors like the microthermal conductivity detector. Because the thermal mass of these tiny chips is so incredibly small, these systems can achieve rapid heating and cooling. That turns an analysis that used to take tens of minutes into something that takes mere seconds.
For field analysis, this is a total game changer. Micro-GC provides exceptional portability. It's used for on-site natural gas energy content analysis, mud logging, and real-time environmental reporting. It's absolutely crucial for trace-level detection of toxic gases like hydrogen sulfide out in the field, and for ensuring biomethane and hydrogen purity, all while sipping just a tiny fraction of the carrier gas that a massive lab unit would gobble up.
And speaking of those carrier gases, this miniaturization directly supports what the industry is calling the green transformation. For decades, GC relied super heavily on helium, which, as you might know, is currently facing some severe global supply constraints. Modern systems, particularly these new microplatforms, are increasingly utilizing alternative carrier gases like hydrogen. This doesn't just speed up analysis times, it vastly reduces the environmental footprint and energy use of the testing itself.
So we've seen this incredible technology evolve from solving murders in a sterile lab to surviving vibrating explosive oil refineries to finally sitting in the palm of your hand on a little silicon chip. It truly is a testament to the relentless drive of analytical chemistry. So I'll leave you with this final thought to ponder. As gas chromatography continues to shrink and its digital intelligence only grows, what hidden chemical threats or vital new resources will this invisible detective uncover for us next?